Hello guys, in this video lecture we will deal with the extreme values of function of several variables. So before starting this lecture I just want to recall in case of function of single variable. So suppose if y is equal to fx be a function of single variable and define on domain. Suppose domain is capital D, then the point x is equal to c is called the point of absolute maxima if fx is less than equal to f of c for all x belongs to domain of definitions. Similarly, the point x is equal to c is called a point of absolute minima if fx is greater than equal to f of c for all x belongs to in the domain. So similarly we can define the point x is equal to a is called a local maxima when we call it is local maxima if f dash a is equal to 0 and f dash a f double dash a is negative, and point x is equal to a is called a local minima if f dash a is equal to 0, but in this time it should be negative. It should be negative. A point where f double dash is 0 and f triple dash is not equal to 0. F triple dash is not equal to 0 is called a point of inflection. For example, if we take fx is equal to x cube, then we observe that the partial derivative, then fx has a point of inflection at origin. X is equal to 0. So if we differentiate this function with respect to x, So we get f dash x is equal to 3x square. F double dash x is equal to 6x, and f triple dash x is equal to 6. Sorry. So here we observe that f double dash 0 is equal to 0, and from here we observe that f triple dash 0 is 6, that is not equal to 0. So double dash derivative at origin is 0, but triple dash derivative is not equal to 0. That means x is equal to 0 is point of inflection. Okay guys, so in this way we can find the extrema, that is maxima and minima of in case of function of single variable. Now we will start with the function of two variable, and we will try to find its critical points, saddle point, and then we will try to find its local and maxima, local minima and local maxima. So suppose we have a function of two variable, suppose z is equal to f of xy. A point a comma b is called local maxima if f of x comma y is less than equal to f of a comma b for all x comma y in some disk centered at point a comma b. Similarly, the point a comma b this is called the local minima if fxy is greater than equal to f of a comma b for all x comma y in some disk centered at point a comma b. So in this way we can find the local maxima and local minima of the given function. So to find local maxima and local minima, so first of all we have to find the critical points, and to find critical points we have first derivative test for local maxima and minima. So first derivative test for local extreme values. So this test says that if fxy has local maxima and minima minimum value local maximum and minimum value at an interior point a comma b of its domain and if the first order partial derivative exists there, then f of x at point a comma b is equal to 0 and f of y at point a comma b is also equal to 0. Now I will give you the definition of critical point. An interior point, suppose a comma b, of domain capital D of function z is equal to fxy is called an critical point if number first both partial derivative, that is fx and fy exist and both are equal to 0. Either this condition satisfied at point a comma b, that is both derivative exist at point a comma b and their values are equal to 0, or if this does not hold, then one or both first order partial derivative does not exist at a comma, then we call a comma b is critical point. Either both derivative should exist, and if they are exist, they should be equal to 0, or either both or at least one partial derivative does not exist. The next we will define here the saddle point. So what is saddle point? A differentiable function fxy has a saddle point at critical point a comma b if in every open is centered at a comma b, a comma b, there are domain points x comma y where fx comma y is greater than equal to is greater than f of ab and f of xy is less than f of ab. The corresponding point a comma b comma f of a comma b on the surface z is equal to f of a comma b, z is equal to f of x comma y is called a saddle point of the surface. For example, if we take the fxy is equal to y square minus x square and fx will be equal to, in that case, minus 2x and fy will be equal to 2y, and we observe that at the origin fx 0 0 is equal to fy 0 0 and both are equal to 0. So the here point 0 0 is critical point. Now we will check, is this critical point is a saddle point or not. So for this we observe that fx comma 0, because if we take a center, if we draw a circle center at origin and if we put y is equal to 0 here, so we get this is equal to x square and this is always less than f00 because f00 is 0 and f0 comma y, this is equal to y square and this is always positive, so it will be always greater than f00, that is greater than 0. So here there are lots of points in this point and this line in which the sometime function is positive and sometime it is negative, so it satisfies the property of this one. So the point a comma b here is 0 0 is also a saddle point. So in this way we can find the critical and saddle point of the given function in case of function of two variable space.